Okay, so your warm-up, don't ask me why, I showed a lot of work here. There's your critical value, don't forget, I always round it to 3 decimal places to get a little bit more of a better, like a more accurate answer. Don't forget you always round up, so I end up with 384, okay? Alright, so today what we're looking at is estimating the population mean. So we're trying to estimate mu today. We're going to look at an unrealistic scenario first, and then we'll look at the more realistic scenario. So the unrealistic scenario is trying to estimate mu when sigma is known. So sigma is your population standard deviation. Okay, so we're going to start with that because it's an easy transition from what we just did. So I still have my 4 steps here. My first one is my state, so what am I going to estimate? I have my plan step here, so I'm using a 1 sample z-interval for means. I'm going to check either that I have a random sample or I have an experiment that did random assignment. I'm going to check my normal check, so my population is going to be normal. My sample size is going to be greater than or equal to 30, which is my central limit theorem. I'm going to check my independent check. So if I have observations from an experiment with random assignment, then there will just be independent automatically. If the answer is no and I have observations from a sample taken without replacement, then I'm going to check that 10% condition. Here's my formula. So again, it's the statistic plus or minus the critical value times the standard deviation of the statistic. Here's my calculator command, and then our interpretation looks the same, okay? So in this example right here, it says the president of a university wishes to estimate the average age of all students presently enrolled. He took a random sample of 50 students and found the average age to be 23.2 years old. Suppose it is known that the standard deviation of all the ages of all the students at the university is known to be 2 years. So calculate a 90% confidence interval, follow the 4 steps. So we want to find a 90% confidence interval for the true mean. I'm doing a 1 sample z interval for means. Random, so yes, it's random. Normal, it says right here, random sample. Normal, so the central limit theorem, so n is greater than or equal to 30, so the central limit theorem applies here. Independent, we took a sample without replacement, so I'm going to assume at least 500 students, which, I mean, it's a university, so I would assume that there's probably at least 500 students. All right, if I wanted to do this using the formula, so I'd have my statistic, in this case the x bar, plus or minus the critical value if I'm doing 90%, 1.645, times the standard deviation of the population over the square root of the sample size. Okay, if we do that math, you get this answer right here. All right, alternatively, you can do it on the calculator. So to do it on the calculator, you'd go over to stat tests. Number 7 is your z-interval. I'm going to use the stat option. So my sigma is 2, my x bar is 23.2, my sample size is 50, my C level is 90. Okay, so everything I just wrote here in pink, you can do it this way if you would prefer. You're just replacing what I just wrote here. Like these pieces, you can do either of those boxes there, okay? And then I have my summary statement. So we are 90% confident that the interval from 22.735 to 23.665 captures, and this is where you want the context, the true mean age of all students enrolled. Okay, to find the minimum sample size, we take the margin of error part, so the critical value times the standard deviation of the square root of n. You solve for n, and we always round up. So in this problem right here, I want to estimate the mean IQ score for a population of statistics teachers. How many statistics teachers must be randomly selected for IQ tests if we want 95% confidence? So 95% confidence means I'm using 1.96. within 2, this is the margin of error. You don't need to change this to a percent. I'm not talking about a percentage or proportion today. I'm talking about the mean. And it tells me this sigma is equal to 15. So I'd plug everything into this formula up here. And I'd solve that for n. When you work all this out, I get this for n, remember, and then I'm going to round it up. That's my minimum sample size. Just remember, when you see those numbers like that, that is the minimum sample size that you could have. But just realize that sometimes what they do in multiple choice questions is they don't give you that exact number. But like out of these choices right here, which one is the minimum sample size I could use? So I know I'm allowed 217. So out of these, if I only had these 5 choices, I'd pick 250 because that's the minimum I can use out of those choices. Okay? All right. If I were here, we'd do an activity. And I'm sure you would all be thrilled. But since I'm not, I'm just going to have to kind of walk you through this. So what's happening here is that what we just did is we kind of looked at this scenario where we're trying to estimate the population mean, but we don't know the population standard deviation. If we're trying to estimate the population mean, we probably aren't going to know that population standard deviation. Like, it's not realistically that we would know that number. So it would be more realistic that we don't know either one. So if we don't know that one, what we're going to end up doing is we're going to end up plugging in this sample standard deviation. So if you standardize a value, so if I standardize the sample mean from the sampling distribution using sigma, that follows our familiar z-curve. If I standardize the value, though, using the sample standard deviation, that follows a t-curve, actually. So they're slightly different here, okay? I'm going to show you a little bit of a video here.
Hi, I'm Pardees Sabeti, and this is Against All Odds, where we make statistics count. Inference is the name of the game when we want to make conclusions about a whole population based on our sample data. In our module about confidence intervals, we learned how to use z-procedures to calculate a confidence interval for a population mean. The z-procedure works in cases where we know the population's standard deviation, but that's hardly ever the case in real life. Now we'll learn a way around that limitation. For times when we don't know the population standard deviation, but want to figure out a confidence interval and do significance tests, statisticians turn to t-procedures. These t-inference procedures were invented in 1908 by William S. Gossett. If you're picturing a stuffy university professor, think again. Gossett was actually a chemist at the Guinness Brewery in Ireland, striving to find the best ingredients to use in their beer. Making ale involves frequent sampling of everything from barley to yeast to the beer itself. Gossett wanted to save time and money by using small samples and their standard deviation as an estimate of the unknown population standard deviation. But using the standard deviation derived from only a few data values doesn't give a sufficiently good estimate of the entire population standard deviation, and so he couldn't proceed with a z-procedure. After much laborious work, Gossett figured out a way around the issue and finally created a new class of distribution called the t-distributions. Let's pay a visit to Pretty Things Beer and Ale.
Okay, so she just talked a little bit about this guy named William Gossett. So again, he was, working on his beer. And what was happening here, so he had these small sample sizes. And he was trying to standardize them using that equation over there that I just showed you. So instead of using like sigma over the square root of n, he's using Sx over the square root of n. He's using the sample standard deviation. And he's finding these values way further out here than he would expect. And if we actually did that activity, that's what ends up happening is we get some of these standardized scores of like 9 and 10, and people are like, oh my gosh, I did something wrong. Well, that's what's happening there with the t procedures, your t distribution. That sample standard deviation can vary so much that when you standardize with it, that curve ends up being shorter and wider. So this is the standard normal one is the blue one. This is the t distribution. As you can see, the way that we denote different sample sizes lead us to these something called degrees of freedom. So the t distribution is a family of curves based on the degrees of freedom. And the degrees of freedom are based on the sample size. But if you notice here, as I increase these degrees of freedom, this curve starts to look more like your standard normal curve. So as that sample size gets bigger, and some textbooks will just always use Z after a certain point, our textbook just is always going to stick with T. But you'll notice here that that distribution is becoming more like the standard normal curve as our sample size becomes larger. Okay, so back over here, if I can bring up my little thingy, it's down here now. All right, so basically, we would have kind of gone through this little activity and you would have seen the differences in the two distributions, okay? So what you need to know here is what's similar between the two distributions. So what's similar is that they're both centered at 0. So if you go back, we look at that this picture over here, even if I change this back to like 1, they're both centered at 0, okay? So the t distribution and the standard normal curve, I'm not talking about any normal curve, I'm talking about the standard normal. Their shapes are the same. So you notice here they're both bell-shaped. This one is a little bit shorter, right? And their spreads are different though. So the t distribution is more spread out because it's shorter. It has there's more area in the tails, okay? So when should you use the t distribution instead of the z distribution? If you don't know sigma, so you don't know the population standard deviation, and you're using the sample standard deviation instead, okay? I kind of repeat myself a little bit here, I think. Or maybe not in your notes, but in my notes I repeat myself. Okay. So when sigma is unknown, so the t distributions, so we standardize, again, when we're standardizing using that SX, we're seeing these values that are further away than what we would normally see if we were just standardizing using the population standard deviation. All right, so that's why Gossett was like, something's different here. I can't use these Z star values that I've been using. Again, we've got our means it's symmetric. They are both centered at 0, but the t distribution, again, has more area in the tails. The standardized, both of these values here just tells us how far, so the t value tells us how far x bar is from its mean in the standard deviation unit. So in sigma x Sx over the square root of n. All right, your degrees of freedom, all you need to worry about is that the degrees of freedom for the t distribution for these procedures is n minus 1. And what does it tell you? It just tells you which t distribution you're using. They're similar, the centers are the same, they're both bell-shaped, they're different, spread's greater because the t distribution is a family of curves. There's not just one curve, okay? All right, so finding t star. So there is a table. You can go through and look at that table there if you want. It should be pretty straightforward if you look at the table. I'll show it to you while I do this one. All right, so again, you always need to know the degrees of freedom. So let's say you want to construct a 95% confidence interval for the mean mu, the normal population, based on a sample size of 12. So you don't know the population standard deviation, so my degrees of freedom here would be 11. So if I was using the table in the back of the book, so the table in the back of the book is kind of, it's nice to an extent, but it's limited, just like all of our tables are. So how this table in the back of the book works is that if you look here at the bottom, it'll like give you the confidence level. So in this particular one, if I want 95, the degrees of freedom are over here in this first column. So I just kind of line up the 95 with the 11 degrees of freedom, and I would get that 2.201 from the book, okay? All right. There's also, you can do this on the calculator, of course. So the way that the calculator works, so you, again, just like before, I have 95% in the middle. So on my calculator, I'd go to second bars, inverse t. All right, this one doesn't have that center right left option, so it's always going to be the area to the left. So you could pick this number over here, so I could do the 0.025. Degrees of freedom 11. It takes a little longer for these numbers to spit out because it's thinking. So there's the negative side. If you wanted to do the positive side, So this line right here would have the 9.5 plus the 0.025, so it would have 0.975 to the left of it. Again, it's going to be symmetric, so this is going to be the positive number. But again, when you're finding that critical value, the formula already has a plus or minus in it, so I just want you just can give me the absolute value of the number. All right, so you can find those two. You should get 2.064 for the one and 3.106. Again, if you notice here, 99 from your Z distribution would be 2.576. So kind of off still. 95 is 1.96. Close, but still off a little bit. Okay? All right, so when we're doing these procedures here, so now we don't know sigma, but we have Sx, so we're going to use the sample standard deviation. So I'm using a one sample t interval for means. So random is the data collected randomly from an experiment that was conducted randomly, same as before. Sampling distribution normal, same check as before. There's a little note here, but I am going to talk more about this in the next lesson. Sometimes we don't have to meet this condition and we can still use our t procedures. Your independent check looks the same as it's been looking. If you notice here, instead of z, I'm using t star. Instead of sigma, I'm using s. You can say sx if you want, over the square root of n. I'm not using 7. This would be 8. My interpretation will be the same. All right, this says what's the standard error of the mean. So the standard deviation of x bar is sigma over the square root of n. That was from chapter 7. The standard error of the mean is just we plug in the statistic instead of using the parameter, so the sample value instead of using the population value, and it's called the standard error. Okay, that's it. That's just our fancy name. All right. Okay. So here we've got an example. Oops, we're going to have some announcements too.
Good afternoon, Fox Chapel area. It is Friday, and we're going to pack up a very strong week. I want to thank all the students that did some dancing and celebrating here in the cafeteria, loosen us up a little bit before we head into the weekend. Just a couple quick announcements, just to make sure that you know what's going on. It's a very busy weekend for our high school. We got the girls basketball team. They are playing Peters Township. We're going to beat Peters Township at Mount Lebanon tonight at 6:30. Again, this is at 6:30, so if you feel like traveling, make sure you go to Mount Lebanon. We're playing Peters Township. Tomorrow at 3 o'clock, actually the boys team that is playing Mount Lebanon, and they're playing at Cannon McMillan. So again, the girls are at Mount Lebo tonight playing Peters, and then the boys are playing Mount Lebo tomorrow at Cannon Mac. Also tomorrow at North Allegheny, we have the diving championship, so please, if you'd like to make your way over to North Allegheny, or you could stay right here at home and go to the varsity wrestling sectionals. That will be tomorrow during the day as well. So again, a lot going on. Do not forget to get
I'm going to have to assume it's a pretty big high school here, okay? All right, if you wanted to do this by hand, so you would have your degrees of freedom would be 249. Okay, so
a fabulous weekend. Thank you.
0.95, I'd have 0.025 in each tail. So T star, I could do inverse T. You could do the positive side or the negative side, it doesn't really matter. We have some music now. There's my degrees of freedom. All right, so if you wanted to round that to 3 decimal places, we'd have to round it to 1.97, okay? So if I was using the formula, I'd have my x bar plus or minus this 1.97, 4.2 over the square root of 250. Okay, if I did it that way, I'd get this answer. If you wanted to use the calculator, so I'm going down to number 8, using the data option. So I'd have 10.2, my Sx is 4.2, 250. You don't have to tell it degrees of freedom. It'll figure it out for you. So I'd write all those things down. Again, this is if you would prefer to do it this way instead of using the formula. Okay, so this work in pink replaces everything I wrote here in purple. And then we have a conclusion like we've had before. So we are 95% confident. The interval from captures the true mean number of hours per week the students are doing homework. Okay, so that's what that one looks like, and that's it.